I am Dr. Amanda Coles from the Department of Informatics, and I do research in artificial intelligence. So I've just got you a little video here to get you warmed up, feeling in the Christmas spirit. So today we're actually going to be talking about Santa traveling around the world. So what can computer science do for Santa? So this is what you're actually going to learn about today. So we're going to look at path planning algorithms. What are they? Why they're hard? What algorithms can we use to solve them? And finally, why do we want to solve them? So that's what you're learning. But what we're actually going to do for the next 15 minutes is talk about Santa. So here's Santa's problem. Santa has to travel around the world to deliver all his presents. And he does not want to visit the same house twice. So we're going to assume that everybody's being good and they're asleep in bed when Santa comes. And he also wants to take the shortest route possible because Santa's got to get around all the houses in 24 hours. We're going to ignore time zones here. We'll assume he can go in any order. So he needs a quick route to get around there. So let's have a look at how many choices he has. So here's Santa. Everybody knows Santa lives at the North Pole. And this is a kind of a reduced version of the problem here where we're just going to say he needs to visit every continent. And you'll see why I'm using a smaller version of this in a minute. So Santa's at the North Pole here. And now he's actually got 6 choices of where to go. So these are highlighted in red. So he could go to any one of these 6 continents at this time. So let's just pick one. We'll pick one randomly. And he's gone to a new continent. So everybody in Europe gets their presents first this year. That's good for us. Now, when Santa's in Europe, he has then got 5 other choices of where he can go. And wherever he'd gone in this map, whichever one he'd chosen, he would still have 5 other choices of where to go because he's been to one place and the North Pole. So again, let's pick one of these choices. We'll take one. Now he's got 4 choices of where to go. And we'll pick one. You guess what happens next. He's got 3 choices, and then 2 choices. And finally, well, he doesn't have a choice. One choice isn't really a choice. He's got to go to the last place he's not visited to make sure everybody gets their presents. And then finally, once he's got there, he's going to go to the North Pole. So let's have a look at what this looks like. So how many routes could he possibly take? Well, in computer science, we often use this thing called tree search. And everybody thinks we're a bit strange because our trees have their roots at the top and their leaves at the bottom. But actually, I discovered during this talk is what we're actually doing is Christmas tree search. Our trees are the shape of Christmas trees. So this is where Santa is. He's at the North Pole. And he had 6 choices of where to go. So these are all the possible continents he could have visited. And from each of those 6, he had 5 places he could go next. And I should really learn. I do this all the time. I try and draw search trees on slides, and I run out of space. So each one of these 5 has another tree underneath it. And that tree looks like that. From each of those 5, he has 4. From each of those 4, he has 3. And from each of those 3, he has 2. The 1 I've left off because you can imagine 1 coming out at the bottom of all those. So how many combinations is this? How many possible tours could he take? Well, it's 720. And this is what we call 6 factorial. Some people call it 6 bang. Any number times all the numbers down to 1 is called that number factorial. So that's great. We had 720 tours. That's not much of a challenge for a modern computer. But each of those continents has, well, quite a few countries in it. And each of those countries has quite a few cities in it. So there is a problem with factorials. I was going to draw a graph, but the numbers draw the graph for themselves quite nicely. So if we've got 2 factorial, we're doing all right. 5 factorial, not too unreasonable. But as you can see, these grow really fast. And the bigger they get, the faster they grow. And when we get to 50 factorial, well, we're struggling to fit it on the slides. So how big could we go then with these problems? How big a set of locations could we possibly hope to visit? Well, let's say a modern computer can evaluate 1 million tours per second. So if you ever see something times 10 to the 6, it means put 6 zeros after it, okay? So the age of the universe is 4, with 17 zeros after its seconds. Okay? So in the age of the universe, on this computer, we can check 10 with 23 zeros after it tours, which means we could exhaustively solve a traveling Santa problem of size 23. Well, that's great, but there are about 25 million households in Britain, and that's 4 with an awful lot of zeros after it times the size of the universe, the age of the universe, to actually consider them all. So what can we do? Santa needs our help. We need to do something. Well, this is a technique we use a lot in computer science. It's called relaxation. And what we do is we make the problem easier. We then solve the easier problem, and we use this easier problem to help us in solving the original hard problem. So let's have a look at how we can use relaxation in this problem. So here is a tour. This is the tour we generated at the start, just by picking randomly which location we were going to go to next. And this is the length of it. It's just the sum of all these distances that we've chosen to take. So now suppose we've started a new tour, and Santa has gone to Australia and then back to Europe. Now we know to complete this tour, he's got to visit at least all of these remaining locations that he's not been to yet. And if we can show, by using a relaxation, that this length plus the length we've already taken is necessarily bigger than that value there that we've already got, then we don't need to consider all those tours. We can get rid of them. So how might we do this? Well, supposing I relax the fact that it's got to be a tour around the world. Okay, so now it's not got to be a tour, but I know I've got to visit every one of these other ones that I've not visited. So I'm just going to pick the shortest path into those, regardless of whether it makes a tour or not. And the real tour either has to take the shortest route, or it will have to take a longer one. It can't possibly take a shorter one. So we know that any tour starting with these two locations is going to be at least this long, which is just a smidge longer than the tour we've already got. So now, without considering all those tours that start with Australia, Europe, we can just ignore them, because we know we're never going to do better having started Australia, Europe. And how does this look with our Christmas tree? Well, if this is when we chose to go to Australia and this is where we chose to go to Europe, we're actually getting rid of this whole tree here, which is a whole 24 tours that we actually didn't have to think about. Now, you might think, oh, 24, that's not a great saving. You know, we have millions and millions. But this is happening all over the place in this tree. And actually, I will convince you that this is good. So these are the world records for, they like to call it the traveling salesman problem outside of December, but for Christmas it's definitely the traveling Santa problem. So these are the records. You can see 15,000 in 2001, nearly 25,000. So this is the number of cities you can explore. 33,800 and nearly 90,000. So this is just using techniques. We know these are absolutely the shortest solutions, and this is just using cleverer and cleverer relaxations to get us a better estimate of when we can get rid of parts of our search tree. So that's very good. But we're still not big enough for Santa yet. We're still not doing well enough for Santa. So here's the moral of today's lecture, which is, if you cannot be perfect, always try your best. That's a good moral for life as well. So Santa can't have an optimal route. He can't have the absolutely shortest route, because we can't possibly check them all to make sure he's got the shortest one. But we can still give him a good one. And the best algorithms for solving these problems, which are too big to solve optimally, is to use something called local search. Now, local search is a very simple idea that becomes more and more complicated the deeper you go into it. So I'll just give you a very quick overview of what local search does. So here's our tour we've generated again. And what we're going to do is we're going to play with this tour. So we're going to take two of the links we've got in this tour, and we're going to take them out. So here we've removed those two links on this side, you can see. And now we're going to join back up the tour again by adding two more links. But there's only one way to do this, which doesn't just put those two links back in, which is that way. And that gives us a new tour, which has this length, which is actually shorter than the tour we had before. So now what we can do is we can keep this tour, and we can make modifications to that and so on. So it's called local search because it's looking at tours that are nearby, that are similar to that tour. And there's nothing to stop you, to force you to do 2 edges. You could remove 3 and join it back up again. You could remove 4 and join it back up again. And that's how we can do local search to solve this problem. Well, if that's the best way of solving this problem, then this is perhaps the coolest way of solving this problem. So computer science likes to take quite a bit of inspiration from biology. So biologists were looking at this problem. Ants, when they're looking for food, quite often, quite uncannily, they will go on the shortest path, and they'll all be following each other along the shortest path to the food and back again. And the question was, how on earth do these ants find out which way is the shortest way to the food? They've not got massive brains that they're using to work this out. So how do they do it? Well, it turns out that first, when the ant's at its nest and it's deciding which way to go, they all go in a random direction. So they all go off. But as the ants walk around, they leave behind them what's called a pheromone trail. And that's like a little scent that all the other ants can pick up on. And the ants that get back faster, the paths that they come back down the fastest, will have more ants coming down them sooner because they've got to the food and they've come back. So the fastest routes will have more ants on them, more pheromone on them. So when the next ant's coming along, well, maybe the millionth next ant or something, he's got a different situation. He's got these routes, and they're marked with pheromone. So if we say red, the redder it is, the more pheromone it's got. Now, he will still choose randomly, to a certain extent, which path he's going to go down, but his choice will be biased. So the more pheromone on that path, the more likely he is to take that path. So let's have a look at how this works then. How does this solve our problem? So here's our ants. They're running around randomly at first, and you can see now the red is the pheromone trail. So you can see they're trying out a few different paths, but eventually they converge on this red path, which is a good solution. Again, the ants aren't guaranteed to be optimal, but they've given us a good solution. Another great thing about ants is if we find out that somebody's staying with their dad on the Antarctic research base over Christmas, and they need presents too, then the ants can readjust. So you can see that because they've got that randomness, they're still exploring different paths, but eventually the pheromone trail gets thick enough so that they end up going around this good path for this good solution with the extra edge in. So that's really nice to see, and it's really nice how we can take from biology something and move it into computer science and use it to solve our problems. So given that we've got these techniques that find us a good solution, how much can we help Santa? Well, here's a solution that was found using local search, I believe. And this is looking at nearly 2 million cities in the world. So that's most of the world's major cities. And the best solution that's been found so far, so people keep working on this all the time and racing with each other. As scientists, we like a good competition to be improving things all the time. So this is the length of the tour that they've got so far, and using techniques of bounding, like we saw before, relaxation, how can we estimate the best tour? We know that this is within 0.474% of the best tour that visits all these locations, which is a pretty good answer. So we could never hope to solve that optimally. Well, maybe one day we'll manage, but that is a pretty good answer to this problem. So Santa's not totally lost. We can help him. And so now I'm coming on to the point of why do we want to solve these problems? Well, actually, we've been a bit frivolous, we've been a bit Christmassy, we've been talking about Santa, but these path planning algorithms, they appear all over the place, and they really are important. So this is a photo of Spirit on Mars. And what Spirit has to do is, well, he has to go to a lot of different locations around the planet, and he has to take rock samples, soil samples, photographs, and so on. And he has a number of limitations, but the two big ones are he has limited battery power. So he's only got as much power as he can get from the sun in the day. And the other one is he's only got limited time. So there are lots of scientists stood there on the ground saying, I want my geology survey done. I want to look at this rock. And so this is an expensive piece of equipment. So the more science this can do in the day, the better. And the way to do the most science is to find the shortest path around all these routes that can get us more science done and more time. So it's not just Santa that needs to path plan. And indeed, there are lots and lots of applications that need path planning doing during their solution. So you can think of the Royal Mail. They're basically Santa all year round, right? They're all delivering packages and letters to us all the time, and they need to plan the shortest path to them to save money, but also there are here environmental concerns, okay? So the less petrol you can use in driving your trucks around, the better it is for the environment. And we've already heard how bad the greenhouse effect problem is, so that's an important one. You can also think of airlines as package deliverers for you. So they need to take people around the world using the least fuel. Big cargo shipping, that's another one. Disaster rescue, this is where time means lives. So the quicker you can get around and make sure you've surveyed all the areas you might need to look at, then the better, the more lives you can save, the quicker you can find people, the better things will be. Circuit board manufacture. Now here's perhaps one that might surprise you, it's a bit of a different problem, is there is a problem with circuit board manufacture too. To make fast chips, we need things to be cool and we need things to be small, okay? If we put loads of wire on, well, that's lots of heat going through the wires. And if we put lots of wires on, it's obviously not small. So if we can work out how to join all the components on a board using the least wire, that's the same problem. How is your data routed around the internet? Well, this is a slightly different problem because you don't want your data to go to every computer on the internet, but it's still a case of efficiently planning a path through the network, in this case of computers, to find a short way to get your data around quickly. Perhaps the most obvious application is your sat-nav. You've got Mars rover technology right in your car there. So how can I get from A to B the quickest? Choosing which roads to do. And there are a lot of roads in the country and a lot of routes you could take. So that's another problem. And the final application I want to talk about, which is a bit of a diversion here, really. It's not a path planning thing, but it still uses tree search. So have you ever wondered how an AI system plays chess? Well, here's how it does it. It starts from the current state of the board, so what does the board look like now? And it says, well, what are all the moves I can do? And these are all the moves I could do. And then, well, given for all the moves I could do, what are all the moves that my opponent could do? And you can keep expanding and expanding that indefinitely. And really, the art of playing computer chess is these trees are worse than the Santa trees, okay? These are really big trees. There's a lot of chess moves you can do. So it's quickly predicting which of these branches is going to lead you most likely to win. So that is how computers play chess, and that is how we do chess with AI. So that's the end of my talk. Thank you very much for listening.